Welcome to Unit 34. It's already late and I have to keep it short. I will talk about four things, and these four things appear in the homework. The first is about Turing's picture. Turing realized that all data we are dealing with actually can be written just as a function which takes values in 0 and 1. So what we have is a sequence, say maybe f1, f2, etc. until fn. So in other words, data are just given by a function. And n is typically very large, maybe 10 to the 13, that's about 1 terabyte. It's amazing how things have changed. When I came here 26 years ago to the US, I still had some information on floppy, and then there were other information like tapes, then hard drives. They are still used, or DVDs, which you use for storing movies. But nowadays you have a lot of information on small things. This is 2 terabyte. And if you look at things which are going into the camera, like the camera which is recording this, so you have little things like that which have 128 gigabytes, which is just totally amazing. You can buy even 1 terabyte such little pieces. And so what we have is kind of just, these are all zeros and ones. And Turing thought about this as a tape, and he had a machine working on this tape, and so could just either move the tape left or right, write or read what is there, write, and depending on the state do things, and prove that this is equivalent to all what we can do with computers. It's totally amazing, the simplicity which you have. And for us in calculus, it's great to have actually data are nothing else than functions. In the homework, you will actually kind of then work with such a specific sequence of data, and it appears in Fermat's room. A movie, and from Spain, a wonderful movie, very mathematical, and you are dealing in the homework with such a thing. But I want first say something about the structure of data, or what form data can take. So we will discuss this more in class. I don't want to go too much, but we have sound, right? Sound, which we have seen is sampled 44,100 times per second, sequence of numbers saved as a file which contains this amplitude. We have pictures. Actually, when you look at the picture, what you have is a red, a green, and a blue value at every point. So in some sense, what you have is, you can, if you read it, you have always blocks of 3 numbers. And so what you have is then, when you look at the picture, like this, you can read it like that, go through this and figure out, store the picture also as a one-dimensional array. So there's the red, green, blue, red, green, blue, red, green, blue, etc. And maybe this is 1,200 pixels, maybe this is 800 pixels, and so you have lots and lots and lots of points. So in this case you would have 3 times 800 times 1,200 bytes if every color is stored by a byte. So that's one picture. But now if you have a movie, for a movie, so what you have is different frames. So this is time. So you have different frames. So it's amazing how much information you have to store. You have to store a sequence of pictures. And additionally you have also to store the sound. So it's amazing how much you have to store. So nowadays, if I'm actually recording this and I have all this camera data and everything put together, it feels about a sixth of this hard drive. It's amazing how much this. And then afterwards it compresses maybe down to 20, 30 gigabyte, which is about 10 DVDs when I submit it to YouTube. So it's totally amazing for me, kind of just to see how much data we can deal with relatively easy. So I will show you the weather data in Boston. If you look at weather data in Boston, and this is the year, and you see the average data, what you can do in order to understand this data, you fit with linear functions, and that's what we have done in the economics lecture. Remember, we have kind of seen that this grows. But it's also very important, if you look at data, how you represent data. You can represent data like this. It might not look very dramatic, or you can just scale it differently, and you can plot it in such a way that the growth of the temperature looks more dramatic. Or you can, if you are kind of a climate denier, you can draw it like that with a very small scale so that you don't see anything dramatic going on. So you should be aware of these possibilities to manipulate data. And there's a nice book, I'm not sure whether I have it here, it's called, I can display it here, it's called How to Lie with Statistics. And so you have to be able to look beyond the data. It's very important that you can do that. And so this is one way to understand data, is just fitting, and another fitting that gives you models. And you can also fit with exponential functions, like if you look at the Fibonacci numbers, and you can fit them with the exponential functions. And actually this is a quite a good fit. So if you plot these functions, it actually works pretty well with an exponential growth. So e to the tx, or at times c. So that's what we call exponential growth. Now I mention this because in the homework you will deal with a model which is more accurate in this respect. Exponential growth is not sustainable. It cannot grow always exponentially. But what you are looking at is the different. This is actually satisfies f prime is equal to af. Now, if you are taking this and you replace it with f prime is equal to af times b minus f, then this will be logistic growth. This will produce logistic growth, and it will eventually kind of just stagnate. And that's typically what happens with populations. I want to end this with a surprise. And that's also something you're doing in the homework, actually for two problems even. What you can do is, for example, you look at the doubling sequence. We will do that in class, maybe a little bit more detail, and you are plotting as a statistician. You might be interested in the first digit. First digit is 1, 2, 4, 8, 1, 3, 6, 1, 2, and so on. You want just to look how these statistics look like, and you will do that with real data. So what you have is, when you look at that, what happens is the one appears with a higher frequency than the others. So what Benford, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what happens is they appear with less and less frequency. Not 10, 9. Digit 1 and to 9, these are the digits which appear. And Benford, so the probability that we have for the kth digit is just the 10th log, the logarithm 10 of d k plus 1 minus the logarithm 10k. But if you look at this book, Mathematical Methods of Classical Mechanics by Vladimir Arnold, he has here on page, this was actually my Bible essentially when I was a student, because I loved the way how he writes, and I still love the way how he writes. And actually he has here a thing in the sequence 1, 2, 4, you know, to the end, the first digits. The number 7 appears with frequency log 8 minus log 7 over log 9 minus log 8 times as often as the number 8. So it is quite an old story, and Benford was not actually the first one who has realized this. But it's a very interesting thing. And if you look at data like tax data or data about what you are doing in the homework, is you look up the population numbers of major cities. You can look at the length of rivers or whatever data you are looking at. This always happens. And this is well known to tax checkers. Kind of, if you are forging numbers and you forge the first digit, you get a distribution which doesn't look like that. A natural distribution on your tax sheet should satisfy this Benford's law. But it's something very. It looks surprising, but it's actually not so surprising if you know a little bit. Just if you look at the data in a logarithmic scale, this is actually then equally distributed. So what happens is, because what happens when you double the things, you essentially translate things. So if you look at this data in the logarithmic scale, this is actually kind of explainable. And that's what Arnold did here. It was an exercise in Arnold's book. But that's just something which shows that statistics is really exciting and data are exciting, and I hope really that you are learning a little bit more. And tomorrow I will also say something about what is beyond this course, like what other courses do make sense. And I highly recommend you learn more about data and data analysis. I myself use this daily.